All right, today we are diving into a classic computer science puzzle. And trust me, it's elegant, it's deceptively simple, and it holds a pretty profound lesson about efficiency that might just change how you look at sorting problems forever. So it all kicks off with this simple question. Take a look at the Dutch flag. You got red, white, and blue. What on earth could that possibly have to do with programming? Well, as it turns out, this flag is the perfect metaphor for solving a really common sorting problem with just incredible elegance and speed. Let me show you exactly what I mean. Okay, so here's the puzzle itself. And at first, it's going to sound almost too easy, but the real magic, as you'll see, is in how we solve it. Here it is. Just imagine you have a completely jumbled list, an array just filled with zeros, ones, and twos. That's it. Your job? Sort it. Get all the zeros to the beginning, all the ones in the middle, and all the twos at the end. Sounds simple enough, right? Now, your first instinct, and mine too probably, is to use what we call a brute force approach. It's logical, it totally works, but as we're about to find out, it is definitely not the most efficient way to get this done. So the brute force way goes something like this. First, you'd go through the entire list once, just counting. How many zeros? How many ones? How many twos? Then, you'd have to go through the list a second time, basically rebuilding it from scratch with the counts you just found. It gets the job done, but it's not great. A huge goal in programming is to touch your data as few times as possible. 2 passes feels a little heavy. And this brings us to the much better way, the optimal method, named right after our visual cue, the Dutch national flag algorithm. Here is the absolute core idea, the big aha moment. Think of the zeros as the red stripe, the ones as the white, and the twos as the blue. Now, the algorithm's incredible insight is this. You don't have to worry about all 3 groups. If you can just figure out a way to move all the zeros, the red, to the beginning, and all the twos, the blue, to the end, what happens to the ones? Well, they automatically just fall into place right in the middle. You only need to actively manage 2 of the 3 groups. So how do we actually do that? We use this fantastic technique that I love to call the 3-pointer dance. We're going to create 3 markers, or pointers, that are going to move through our list and sort it perfectly, all in a single pass. Our first dancer is the low pointer. It starts at the very beginning of the list, index 0, and its only job is to mark the end of our sorted red section. Everything to the left of low is a guaranteed 0. Next up, our main character, the star of the show, is the midpointer. This is the one that's going to do all the hard work. It's going to move through the list element by element and decide what to do with every single number it finds. And finally, holding down the other end of the list, we have the high pointer. It starts at the very, very end, and it marks the beginning of our blue section. So everything to the right of high is a guaranteed 2. And this little condition right here, this is the engine for the entire algorithm. The dance keeps going as long as our midpointer hasn't passed our high pointer. The second they cross, we know every single element has been inspected, and boom, the list is sorted. Okay, this is the core logic. It's so simple and so beautiful. As our midpointer scans the list, it just follows 3 simple rules. Rule 1, if mid lands on a 0, that 0 belongs at the beginning, so we swap it with whatever is at the low pointer. Then both low and mid take 1 step forward. Rule 2, if mid finds a 1, well, the ones belong in the middle, so it's in the right spot, for now. We do nothing. We just move mid 1 step forward to look at the next number. And finally, rule 3, if mid lands on a 2, that belongs at the end, so we swap it with whatever is at the high pointer. Then we just move the high pointer 1 step to the left. That's it. That's the whole dance. And the result of this elegant little dance? We get a time complexity of O of n. Now that's just a fancy academic way of saying we solve the problem in linear time. It means we only have to look at each element in the list 1 time to get the whole thing sorted. For this problem, it is literally impossible to be more efficient. But, why is this one little puzzle so important? It's a neat trick, sure. But the reason we study it is because it teaches us a massive, fundamental concept in computer science, the power of partitioning. What we've really been doing this whole time is called partitioning. We're just taking a collection of stuff and rearranging it into groups. In our case, it was the group less than 1, the group equal to 1, and the group greater than 1. This idea of partitioning is a cornerstone of so many advanced algorithms. And why does that matter so much? Because this partitioning logic isn't just some theoretical concept. It is the absolute core, the engine that powers QuickSort, which is one of the most widely used and efficient sorting algorithms ever designed. When you understand the Dutch flag problem, you're actually understanding the very heart of how QuickSort works. So let's bring this all home. What is the big lesson here? What's the main takeaway from this elegant little problem? Well, we learned that the obvious solution isn't always the most efficient one, and a really clever approach can cut down the work dramatically. We also saw how a powerful visual metaphor, like a flag, can make a complex algorithm feel totally intuitive. And maybe most importantly, we learned that this one simple puzzle reveals a universal computer science principle, the incredible power of partitioning. And that leaves us with a final thought to chew on. This pattern of partitioning, of dividing a problem and putting things into the right buckets, shows up everywhere in programming and in life, really. So the next time you face a really complex problem, just ask yourself, is there an elegant solution here that's really just a clever way of sorting things into the right groups?